Hello and welcome to our this week's review video. Today we'll be looking at two semiconductor processes. The first one being photolithography process. Now the photolithography process is we just put on our pattern mask on our wafers and we just shed a rays of light on it. So when the process ends, we have our wafers with our mask patterns. So depending on a mask pattern, we could get infinite results on our desired wafers. The next thing I have to note is now depending on the various wavelengths of light, we could have a more detailed pattern on our wafers. Meaning the more shorter the wavelengths we use on lithography process, the more minimum pitch size and smaller device we will end up with. On our conventional lithography, photolithography, the maximum sharpness or the maximum wavelengths we can get is argon fluoride, which has a 38 nanometer wavelengths. But however, if we go into a realm of EUVs, extreme ultraviolet rays, which uses tin to gain light and some collection of mirrors to collect some of the light, we could have a whopping number of 13.5 nanometers. Finally, I'm going to talk about a double patterning process. As I mentioned earlier, there exists some limits to our wavelengths of light, so we simply do a lithography twice to gain a minimal pitch size. The first step I'm going to tell you is the LE approach, the litho-etch technique. I will show you a picture right here. It's really hard to draw, so I'm just going to give you a picture. It is used as a repetition of litho and etch techniques. Nothing special, just very simple combinations of processes. Next one I'll show you is the self-aligned double patterning process. This one's kind of more trickier than the previous approach because it uses spacers. The spacers will perform as our kind of a second mask or as a shield on our next second lithography and etching process. And this, hence the name self-aligned double patterning. This is it, and thank you for listening, and I will see you on part 2.